Okay, so what I can do is I found here an old example exam. I don't know from when it was. It's quite old, 2016. So I will distribute at some point an example exam. But this here is not all relevant. So the course has changed its content a bit. Some of these questions are not really that relevant anymore. This stuff, yes. Yes, yes. Yes. So here it's all dealing with Astral. So this is a programming language that used to get taught in this course, but we don't do anymore because I don't know it. And it's stupid. Following for programs where they are reactive. Yeah, see, we don't do this either. Signal diagram, Astral, transition systems, we don't do anymore. We also don't do this anymore. All this. This we do. So we can start working through some of these questions, or just people ask me questions. I'm not going to work through them now because I'll probably start doing that at 1:30. Sorry, my 1:30, your 7:30. But let's take inspiration from what's on the screen for you guys to ask me some questions. So embedded systems, how are they different from like normal PCs? So we saw this all throughout like sort of the explanation of what an embedded system is, like on a hardware level. Like, you know, we have hardware limitations because we're on a smaller device that's energy constrained, resource constrained. But then we also have, for instance, on a software level, difference because we're cross compiling, and then we have essentially the boot up sort of the boot up sequence is different. We don't load the program into the kernel of the operating system like we would on our laptops or our desktops, but we then put it into a certain region in memory, which is run when the microcontroller is powered on, sort of thing. So there's some differences both on a hardware and on a software level. So you should have a basic understanding of these differences. I might ask you to sort of explain to me the boot sequence of an embedded system, for instance, or how it differs from a like a computer. Real time and soft time. So maybe the difference between even soft time and hard real time. So hopefully you guys know the difference between them. We talked about them quite extensively. And real time, of course, being a reoccurring thing throughout this entire course in lots of different fields. So then we get down to sort of compilation and cross compilation. This is the whole compiling process. Now, something we did spend more time on than in this, like back when in 2016, this course was a lot more theoretical, and we've tried to make the course more practical. So we tried to really look at the compilation process. And back then it was sort of just say, okay, we compile for a different architecture, and that was it. But now, since we've learned a bit more about, you know, compiling, pre-processing, linking, hopefully you guys can sort of maybe give me a bit more or shed a bit more light when I say, what does cross compilation mean? Saying, well, the assembler in the compilation process is going to produce instructions that are targeted to a different instruction set architecture, or ISA, which is what Daniel was talking about. So the pre-processing of the files is the same. The compilation of the files is generally the same. That's more so based on the compiler or the version of compiler you're using. But the cross compilation is more so in the generation of machine code or generation of assembly code, because this assembly code or the instructions in the assembly code have to match the architecture that you're targeting. So that's what cross compilation is, when you're compiling it on like one architecture for a different architecture. So when I want to compile a program for my microcontroller, I'm compiling on my x86 laptop for instance, a RISC-V microcontroller. So I'm compiling on one ISA for a different ISA. This stuff we didn't do so much, I like at all. And so here we get down to an ISA and what the ISA stands for. So this is what Daniel went through, that sort of we have this ABI, this application binary interface, and it specifies the sort of how the binary machine code has to function, like how it uses the CPU and the registers, and it's sort of the machine code or the assembly instructions that the processor actually supports. No, there is usually a whole family processing. Yes, exactly. So this, for instance, the second question here is very accurate in that, for instance, there's a large range of ARM microcontrollers. You have like the M4s, the M7s, the A5s, the A12s. There's so many of them, but they all have the same instruction set. They're all ARM instruction sets. Name 3 different programming models. Nah, we didn't really go into that. Architecture stuff, single. Yep, so you guys should have seen all of this. Which of the architecture types in the previous questions require the least amount of functional blocks? Which one requires the most? I don't think Daniel quite went into it like this, so this is probably not something that you would get asked in the exam. Name and explain 2 different hazards. This you'll most definitely get asked, to be able to describe the different types of hazards that you'll get in a CPU or in a pipelined CPU. And this is what we went through yesterday. So we maybe will do, or this is like almost the exact same question. Holy shit. Maybe exact same. Maybe I took my inspiration from here last year. And this we haven't seen before. Mark basic blocks above the drawing lines. Draw the control flow graph for the BBs, assuming that no compiler optimization takes place. Use distinct signals. Missing lines, -1. Okay, so this is the marking comments. Formulate the control flow / structural constraints. Formulate the logical constraints. Why is it easier to determine the worst case execution? Oh, okay, no, this is not us. Which instructions are grouped into an L block? So this is where it will get a bit interesting for you guys, because I don't think many people understood this. And yeah, the formulas that we need for the ILP. Estral. No, we didn't do any of this. Neither did we do this stuff, except we did do fixed point computations. Yeah, so maybe we'll do one of those today again. So unless anyone's got any questions, I'm just going to shut up and wait for past instead of just talking to myself. So don't worry about missing this because this will all go up online. But I just want really people to ask me questions. So I'm generally just going to skip things or assume you know it unless someone says, hey, can you explain this? Because there's enough content for me to explain for 1.5 hours that I have probably want to skip stuff instead of explaining every single detail. So we'll get cracking into it. Sort of the very beginning, this is sort of going from the introductory lecture where we discussed like embedded systems and sort of how their characteristics. So does everyone understand the difference, or how you would explicitly explain to me the difference between an embedded system and a general purpose sort of computing system such as our laptops? Okay. So then we looked at, for instance, we are interested in this course. This is also from the introductory lecture that we're interested in real-time systems, embedded systems, or just real-time systems in general. And what real time means. And so this is sort of this this awareness of the passing of time that is explicitly linked to the system's operation. Like for instance, we did it all in FreeRTOS. We're doing delays because of times. We're doing blocking on certain signals because of times and durations in milliseconds. And we, for instance, saw in scheduling, we're scheduling based off of time deadlines. It was all throughout the course. So this is what real time is, and this is something you should really understand because it's popped up a lot. Then we sort of dealt with the different types of real-time systems, namely hard real-time and soft real-time. Sort of a question that you could expect to get hit with, sort of the difference between non-critical and critical systems, essentially. So is everyone good with all of this? Okay, great. And then we moved on to compilation. And so this is something that you can expect to be asked of you more so than just this year, because in this year there was not much of an actual look into the compilation process, whereas we spent like half a lecture on it. And so you should all be quite aware of the compilation process and the sort of the steps of the preprocessor, the compiler, the assembler, and the linker. Now, I can also recommend that this sort of information is like abundant on the internet. I'm sure if you typed it into YouTube, there'd be a heap of people with much more like polished explanations of it than what I gave. So I would maybe just spend an hour or two just browsing through YouTube, watching sort of these explanatory videos. But you should have a basic understanding of how the whole compilation process works, and then also in terms of compiling for a different instruction set or different architecture. So there's cross compilation. You should understand what that means, because this is something that is a large part of embedded systems. I mean, without cross compilation, we couldn't program embedded systems. So is everyone savvy with what the compilation process and cross compilation? Okay, great. Now, we didn't do this in ours, so here we have the instruction set architecture. This is going into the processor architecture. So the ISA is the instruction set architecture here, which we saw, and Daniel was sort of explaining this. He was using the RISC-V architecture, which has its own ISA. And so this is sort of the set of instructions, the assembly instructions, which we saw examples of. So you should all be quite familiar with that, I hope. And so is everyone good with what the ISA is? Okay, great. And then we're sort of dealing with, this wasn't so much what we talked about, but like scheduled and time triggered, these are things that came up in the scheduling lecture. So you should maybe sort of be aware of them. Sort of we have this schedule of events. And then we also have, like we saw this in FreeRTOS, meaning that we actually create tasks with different priorities that get then scheduled onto the CPU. But we also have triggered events, meaning that some task was waiting for a semaphore, which could have been the result of an interrupt. And this would be a triggered event, right? This unblocking of the task would be the result of some event. And therefore, it's event triggered. So the different types of CPU or architectures that we dealt with. Single cycle, which we briefly sort of looked at, where we have this sort of the frequency or the clock tick is designed such that the longest executing instruction of the system can execute in that one tick. So therefore, each instruction takes one cycle. They have very low clock frequencies. Yeah, so everyone good with this? Then a multi-cycle is essentially when an instruction can take more than one cycle to finish, but we do not have pipelining. So we can break it up into stages, but we don't pipeline them. And I'm sure you're all aware of what pipelining is, since we dealt with it Daniel dealt with it in multiple sort of portions. We have it in the buses, we have it in the instruction, like in the CPU instructions, and pipelining is very dominant or a very predominant feature in making hardware faster, right? So we should all be good with what pipelining is. This we didn't do, so don't worry about this. Now the hazards. This is something that I imagine, I can't speak for Daniel, but I would imagine that he would ask you to sort of explain the different hazards that we can get. I know that in the course at TUM, it's always pretty much been a question in some shape or form. Maybe to give, for instance, data hazards. There's multiple types of data hazards. I think there's like 4 of them, to sort of be able to explain them. Now, I don't think they're extremely hard to sort of learn because they sort of make sense, but maybe just spend a bit of time learning the different types of hazards. Again, this is a very large topic in computer science, and if you punch this into YouTube, you will find an abundance of videos explaining these, right? So these sort of hazards you should be aware with. I don't know if I can off the top of my head explain them. It's been a long time since I actually studied them myself. And then we're going to get to the cache questions. And I imagine I will come up with some sort of a question similar to what we did yesterday in the tutorial, but I'll maybe phrase it in a way that makes you sort of think a bit. Generally, if you understand the concept of direct map cache, meaning that we have the offset, the index, and the tag fields of the memory address, we have then the cache, which is made up of cache lines, and a cache line has metadata that stores the current tag. If you understand this and what we did yesterday, I'm sure that you should be fine. These questions are really just sort of about thinking logically about what we're missing. Like, okay, we don't know how many offset bits we have. What do we have? And what can we calculate to sort of figure this out? And you have to systematically think about what we've been given and what other things that we can figure out from what we have, right? So is everyone good with these calculations? I think this is almost exactly the same question as what we did yesterday. So if we have time today, I might do another one of these quickly. I'll find a different one for us to do that has different values because we did this yesterday. So then we get into the stuff that we covered today. The worst case execution time, which I might also, I will upload one example, like sample exam, that I will also give the answers to. I will make it, I haven't written the exam for this semester yet. And when I'm writing this, I'll make probably a compacted version of it, right? So you can expect the actual exam to be a longer version, just because I don't have that much time that I can write 2 full 90-minute exams for you guys, because I actually don't get paid to write them. So this, for instance, will be something that we looked at today. Like we have to mark out the basic blocks. So go through and put lines in there and sort of make the segments. So exactly this, like mark on this thing, the basic block boundaries. Then, for instance, draw the control flow graph. So this is what we were looking at today before we got to the cache conflict graph. We're sort of just looking at how the program actually flows between its basic blocks. And then we can sort of from that, we can then do what the next question probably asks exactly, and we can formulate the control flow constraints. So this is this list of like x1 equals d blah 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 plus d blah blah equals d plus whatever, right? And then the logical constraints. And so this one's a bit tricky. It's sort of hard to teach this in a way. It's sort of, you have to look at the program and say, okay, sort of understand the code. So for instance, here, we could see that I is getting incremented. And I, for instance, here is 0. So we could know that this while loop is never going to run more than 3 times. So we could say that whatever basic block this falls into, its x blah, blah, blah is less than 3, right? Or it is 3, because it's always going to run 3 times unless there's some way for this to not, right? And so then if we were to look, for instance, this is dependent on found being equal to 0. So we have found equal to 1, and then this sets it back to 0. So as long as this condition is held true, then this will keep running. So if we figure out how many times this runs, then we can figure out how many times this, this basic block would actually execute. And this would be a logical condition. So if blah, 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 this would take too long to now analyze. So these are really up to you for just thinking logically. I almost find them challenging myself to do. And this is not relevant. We didn't do Astral. Yeah, so this, for instance, an L block, as we discussed today, is this sort of smaller grouping of a basic block into its cache lines. And so we, for instance, did this example with the yellow and the red cache lines. And so we could then say, like, this is 2 L blocks. This basic block is comprised of 2 L blocks. So what's this question? Which instructions group into an L block? How many possible execution times does a single L block have? Okay. And so an L block is, so it's all instructions in a basic block that belong to the same cache line, which we saw today in the example. And there are 2 possible execution times, which is, namely, we know that they will all have the same cache characteristics because they all get always run together in the same cache line. So if the first one is a miss, then the block gets loaded and the rest of them hit. Or if the first one's a hit, then they're obviously all in, then they're all hit. So essentially, it's only a hit or a miss on the first instruction. And these are the 2 characteristics. So we have the first instruction is a miss, all a hit, or the first instruction is a hit, and then all others are a hit. Sorry, what's going on out there? Anyway, so do we understand this? I have this feeling that people might not understand this because the L block stuff today was a bit, Okay. Then the next question, essentially just regurgitating the objective function from the lecture slides for the ILP. Now, if you can explain this to me, maybe in a sentence, this would also be useful. I could do something like this. And we can see that the worst case execution time is the maximum of the sum of the execution time and the execution count of each L block if it hits and if it misses, because those are the 2 possibilities that it can have, that we have the hit execution or the miss execution. So we need to calculate how many times will this basic block execute as a hit, how many times will it execute as a miss, and then we can sum them up with their execution count, with the execution times for those conditions. And then that's the sum, and we want to find the maximum of this. And so this is the objective function that, given the constraints that we provide to the system, the solver will go and solve for us. So if you can explain this formula to me, or you know this formula, then this is also something that would be good for you, right? And this is all Astral, which we didn't do. So this is model checking, which we also got rid of in the course because it's completely irrelevant for bachelor students. And scheduling. And so this is also something that we did. And so maybe I will do, I can even do this exact example. because it doesn't have well, it does have the answers, or is it a different one? No, let's work through these ones. So then I'll do these as well today. So I'd say in the next like hour or so, I'll do a scheduling question. What was the other ones we wanted to do? A cache question, a worst case execution time question. The rest of the stuff as far as C programming, I don't really want to re-go over that. Maybe if you want to study, then maybe try and work through the project a bit in your own time, because if by doing it, like really learning a programming language, you can't study it so much as you can just practice it. So maybe sit down and try and work through it. Online, there are like a absolute billion C tutorials. Do any of them. I'm definitely going to ask you some questions to do with basic C, like explain to me what a pointer is. If you have this pointer, how do you dereference it? Like, hey, here's a pointer to a structure. How do I access this member? This would be an example of a perfect example of a question I could ask you, or explain to me in words what a pointer is. How do I formulate a function? How do I return a value from a function? These sorts of things. So really just like the stuff that's in the slides. After doing all the tutorials that we did today, I imagine if you go back through the slides, the things will make a lot more sense. Because like, oh yeah, I've seen that. I know what that does. Okay, so then let's do this example at the beginning. So let's move this to the correct screen. Oh, where's this document located? Course material, source, extra exercises, exam. Okay, great. So let's open the scheduling lecture notes as well. So we have a reference to the formula, because I think I could remember them, but I'm not 100% sure. But these are something that you'll need to make sure that you know. So this is, for instance, the fixed point formula that we saw, that we also worked through some examples. But let's look at this question first. What does it want exactly here? I think I have some posts. I will have to be back in a minute. 1 second. Okay, so let's do this question. Consider the four tasks T1 to T4 with deadlines equal to periods having the following periods and worst case execution times. Execution times, pretty much. So we saw a similar thing in our example that we did in the tutorials. Why can't this task set be scheduled on a single CPU? So we know from the lecture that we have this fixed point computation that we can do to determine if a task set is schedulable. So we could start by doing this, a fixed point computation, but it's quite long because we have to do it for each individual task. And if all of them are, have a response time less than their deadline, then we know that they're all schedulable. But there was this initial test that we can do, which is quite easy, which is namely that the sum of all of the utilizations is under one. And if it is over one, then it's not schedulable. So we, for instance, can do this straight away. I imagine this is what this question is asking for. At least I hope it is. So we know that the utilization equals execution time over task period. All right. And so if the sum of utilization times for I equals set of tasks is under less than or equal to one, then maybe where's my mouse? Come on, may be schedulable. So it's not enough to do this by itself to say it is schedulable, but it is enough. If this fails, we can say it is not schedulable. So it's good for an initial test. And why I think this question only wants us to do this, because it's asking why can't. And it's straight away saying, okay, prove to me that this is not schedulable. And the only thing that this equation can tell us for sure is that it's not schedulable. So let's look at these. The deadlines equal to periods and having the following periods. Okay. Well, we don't even need the deadlines in this calculation. So let's do A. And it's going to be the sum of the utilizations for sum I, we'll just do a task set, equals EI over TI. And so this is going to equal for T1, like for instance, we'd have 2 over, what is it? Have the following periods. So in this case, the period is given as P, not as T. PI. So this is going to be 2 over 4 plus 5 over 25 plus 20 over 30 plus 4 over 10 plus 6 over 12. Now, by looking at this straight away, I can tell that this is like way more because these two here give me 1. And so like it's clearly over 1. So I really don't even need to say I can, well, let's sort of roughly figure out this is 0.5. This is what, 0.2, 0.33 plus 0.4 plus 0.5 equals approximately what, 1.61.93, right? And so this 1.93 is not less than or equal to 1, therefore not schedulable. Okay, makes sense to everyone? Great. So what is the minimal number of processes necessary to schedule this task set? I imagine. So how many schedulers and processes do we need to schedule this? If every processor gives us 1 utilization capacity, Should be pretty easy. It's just 2, right? Because then if we have two CPUs, we can maybe be schedulable if the sum of the utilization is less than or equal to 2. So each CPU gives us 1 utilization, right? Like 100%. So this is the same as saying utilization is under 200%. So given a valid possible mapping, which task TI runs on CPU to assign priorities to each task such that they can guarantee that all deadlines are met. Now this is quite, I think there's a trick to this question. In that, oh wait, maybe it wouldn't be. Give a valid possible mapping. It's actually a bit of a tricky question. Think about that one for a second. So I don't think I would ask this question because this is way too old. Given a valid possible mapping. I think it was saying that rate monotonic which one was it? The ideal. Here, the optimal schedule. Earliest deadline first. Although it's a dynamic schedule, so it's not applicable for us. Such you can guarantee all deadlines are met. Given I think we'd have to draw it out to figure it out, but that would take too long. So I'm going to skip it because I'm not going to ask this question. But we'll then move to 24. So this would be C. The steps would be to split the util between cores. So if you are interested in doing this, such that each core is under 1 util, then draw a timeline and see how you can meet all deadlines. You could also do a fixed point computation. So for part B, was it from part A you drive? Yes, because in part A, we've derived that we have a utilization of 1.93. And how many CPUs would we need? So if you have, each CPU gives you essentially 1.0 of utilization, right? So a utilization of 193, this is equal to 193% utilization. One CPU equals 100% utilization. Therefore, we need 2 CPUs to have the capacity to fit 193% utilization. And this is why you'll see on computers, if you're looking at like task managers or something, I wonder if maybe it'll show up on my top. Here somewhere, it might say that I'm using like 200%, 300% utilization because I'm using more than one core, right? if we just look at the question is, what is the minimal number of processes? You can't have 1.9 processes. Like I can't put 0.9 of a CPU on my computer. I need a whole CPU, right? And so this is why we need two CPUs. Two CPUs. Two processors. Right? Okay, then let's go down to 24. I wonder if I can delete this stuff so we can do it via hand. No. It's kind of annoying. But what I could do haha. Great. So let's run through this question now. Given the following set of tasks, use a fixed point computation to compute the response time of 3 tasks, assuming a fixed priority preemptive scheduling, T1 having the highest and T3 having the lowest priority, right? So we know that this is T1 highest. Wait, what is this weirdness? Okay. So this is the highest, lowest. So the priorities. Now, normally, if I asked you in a question, determine if this is schedulable, then you would firstly go and do this analysis. But this question has explicitly asked us to do a fixed point computation. So we won't do the utilization less than one test. Although I might ask you, hey, check if this is schedulable, and you can go and do the fixed point computation, but it might have been enough to just do this utilization test, which takes a fraction of the time. So be aware. So what we have to do, we have to do the fixed point computation. We'll start from the lowest priority task and we'll go up to the highest one, because the lowest priority one is the quickest to, we'll start from the highest priority task and go down to the lowest one, because we know from the formula that when we're doing it, we need the set of all higher priority tasks, meaning our lowest priority task has the most complex formula to finish, meaning it'll take the longest. And we only need to prove that one of the tasks won't meet their deadline, and then that's enough. We can stop. So we'll start from the easiest, and if the easiest can't be met, then we don't have to do the rest of the computation. We can just leave it and say, yep, this is enough to prove that it's not. So we'll start with T1. And the formula is, let's copy it over so we have it as a reference. This is something you will want to remember. So start with T1. Now we know that the first iteration, so the response time for instance, I here is 1. So this is I equals 1. It's because it's task 1. So therefore we have R1, the 0th iteration. So this is my first iteration. And this is just equal to the, because you imagine here, for if n equals 0, then this equals 0, right? Then this equals 0. So this is essentially just EI, which equals 2. So that's the first iteration done. Now we'll go on to the second iteration. So this is, R1, 1, which is equal to EI plus the sum of higher priority tasks. But this is the highest priority task. So this is essentially just the sum of nothing. So we'll just get rid of that. And so we can see that this will just be 2 again, right? So for the first one, we have the 2 consecutive iterations that give us the same number, so we can stop. The highest priority task is always pretty much just going to be super simple. It's just the execution time. So therefore, we know the response time. Therefore, response time of task 1 equals 2. And what did the question say? Assuming fixed, and the period is 5. So this is the deadline. Therefore, R1 is less than P1. Therefore, schedulable. So far, we're on a schedulable system. Nothing's failed yet. So we'll go down to task 2. So R20 equals execution time of 2, which equals 2. Now R21 equals E2 plus, then this is the sum of high priority tasks. So the ceiling of R20 over TK. And so this is going to be the highest priority task is task 1. And so this is, in our example here, this is, let's put the squiggly, equals the PK, right? This is the period here. Equals period of task 1, so over 5 multiplied by, we'll put this in the actual word for it first, P1 times by E1. So this equals out to be 2 plus the ceiling of 2 over 5 times by 2. So we get, what's this? The ceiling of this will be 1. So we get 4. And if we do the next one, 2 equals essentially 2 plus the ceiling and 4 over 5 times by 2. So this also gives us 4. So we can stop. Therefore, response time of 2 equals 4. R2 is less than P2, therefore schedulable. So far, so good. The last task, and where it's probably the most likely to fail, right? Because this is the guy that's getting ignored and neglected. So time task 3, and this is equal to what I have in front of me here. This is 8. Now, second iteration, E3 plus the ceiling of R30 over P1, E1 plus, because this is the sum, R30 over P2, E2. And this here oh wait, you said yellow was a bad idea. This, this is the sum over all higher priority tasks. So we have equals 8 plus 8 over, what's P1? 5 times by 2 plus ceiling of 8 over P2, 10 multiplied by 2, which gives us, this is 2, so 8 plus 2 times 2 plus 1 times 2. So 8 plus 4, this gives us 13, 14. Right, 2, 6, yes. So let's go and do the next one. So R3, 2 equals 8 plus ceiling of 14 over 5, 2 plus 14 over 10, 2 equals 8 plus, and this gives us up to 3 times 2 plus 2 times 2. So what does this equal? 6, 10 equals 18. So next iteration. And I imagine that this will eventually sort of hit a steady state, but we can already see, oh wait, no, we can't see already because our P3 is 30. Shit, it means we have to keep going. Ugh. He will hit a steady state. Awesome. Plus 4 times 2 plus 2 times 2. And this also gives us 20. So we've hit steady state. So we know that response time of 3 is 20. And R3, yep, R3 is less than P3, therefore schedulable. And since all three tasks were schedulable, the system is. Also is. Yay. So that's the end of that question. Any questions on that? So if any of them fail, yep, then it's not schedulable. We only need one task to fail, and then we know we can't be scheduled, right? And it's most likely going to be your lowest priority task. Okay, so I'll save this. And you guys can have this exam as well. Make a but please be noted, like be wary that portions of the questions in this exam actually are not valid. Maybe what I'll do is I can quickly do this. This is stuff that we didn't do or we won't need. Okay, great. Now, where was this other question that we could do? So we could also do this one here, except for the logical constraints, because that will take me too long. All right, so let's work through this one. Now, maybe you guys can give me a bit of input on this one because I think it's fresh in your brains. Where's my first line? Between which lines? When I'm marking my basic blocks. Come on, someone's going to know this. How about here? Nope, yep, nope. Very good, no, Chen and Jones, I guess. Very good. First one. This is BB0. And my next one. Chan, you were crushing this before today. Yes. Next one. Keep going, man. You got this. Oops. Where's the next one going to come in? This is a little bit tricky. That will be one, but you're missing one. Think about a basic block has to be a set of executions that always get run together. So when we go into this while loop, we're always going to run the if statement. But we might not always run found equals 0. So, oops, shit. We're going to have here BB4, BB5, and I think you can do the rest. Mm-hmm. And then obviously that's the end, BB8. So we have 8 basic blocks. Now let's draw the control flow graph. I'll do it up here on the right because it'll be easier for us to see. All right, so now we've got all of our basic blocks. Now we need to draw them. So we're going to have our first basic block up the top. And we're going to go down to our last basic block at the bottom, which is BB8. So the first one, I think this one's pretty obvious, hopefully to everyone. We'll just go down to BB1. That's why the first line, second line is not considered as your BB0 and BB1. These ones, like the actual function definition, like the function is not really like if you think of the function as code, like you go into the function, it's just it gets executed. Like you can't branch on it or anything. Like it always just runs through. Like you enter once, you come in. Oh man, I hate this. You come in once. You're not going to loop back up to the function name, right? So if you ever enter the function, you'll run these first 3 lines essentially the same. If we're thinking on a source code level, this will look different on assembly, but we're dealing with source code basic blocks. So you can just pack the function name into the first basic block pretty much. So then let's look at like this next little bit's a bit tricky, right? So this while loop ends here. So what are my options going to be now going out of BB1? Yep, that is definitely one. And what else? You are right. Well done. So going from 2, we'll then pretty much, I think hopefully it's obvious that we can only really go to 3. But from 3, we have again 2 options because it's a while loop. So we have like the exit condition and then the, condition, right? So 1 to 3 to 7, 3 to 7. Yes, so that's on the fail condition. So I'll put down BB7 here. So this is the non-condition. And then the other one would be 3 to 7, 1 to 8. Wait, no, that's from the last one. Yep. 3 to 4. Yep. Now this is where it got a bit tricky for you, right? In defining the basic blocks. How does it now look? Like what does my next sort of little bit look like? No, not quite. We're not quite there yet. Let's just look at leaving basic block 4. Four to 5 and 4 to 6. Yes. So I think this is the bit that sort of confused you because we also need, where's my mouse? We'll have 4 to 5. This is going to be a bit squishy. We'll have basic block 6, and over here we'll put like basic block 5. Now basic block 4 can go to basic block 5, and then it will go to basic block 6. Or we can just jump straight to basic block 6, right? So this orange path here, it's probably really hard to see. Let's make it more visible, more high contrast. The green path would be this little, going down to found. And if the condition didn't go, then we would jump, let's say, the pink path just straight down, and that would be this guy. All right, so this, I think we're good now, hopefully. But we're missing some connections now. So now we get towards this like 7 to 1. So this is also, let's see, 7 start, would go back up to the while loop because the while loop has to exit. Meaning, so 7 will go up to, where you say 1. Yes, that's the correct one. 7 goes up to 1. Yeah. And what else? We're going to have another, we're missing another one as well, I think. Yeah. So from, what else are we missing? 6 to 7. No. Think about a while loop. A while loop just doesn't exit. Yes, you have to go back up first, check the condition, and then you exit. So we have 6 to 3. So if we are, like, we'll go from this I++, back up, we'll do the I evaluation one more time, and then we'll go down to BB7, right? So I believe we now have all of our arrows in our graph. So now, if we look at the question, is everyone good with just drawing this now? So what the question asks is us to also use distinct signals, symbols D0, D1 for the edges, because we're going to need this for the constraints. So we're going to go through now and put in just random A0, A1, A2, A3, A4, A5, A6, A7, A8, A9. We have that one already. And A10. So it's hopefully all of them. Have I missed any? No. Because now I will copy this just so I can look at it on the same screen. And we will go down to the next question, which is formulate the control flow / structural constraints. So what are these constraints? If we have as well, we're going to need, sorry, we forgot to put in these variables x0, x1. This is the execution count of the basic block. So you'll need to also put these in. Don't forget them. There we go. So now with those variables there, let's do the structural constraints. Can someone give me one of them, or the first one ideally? So if we're looking at like, we should probably also put in, for instance, this is a bit of a mistake of me again. I should have put in an incoming signal, and I'll call this, like, let's just call this A11, and leaving A12. So let's start looking at the constraints. So looking at x0 equals A11 equals A0. Next basic block, x1 equals, what does it equal? So we've got A0 coming in. So the same coming in has to equal that coming out, but we also have A10 coming in. And this has to equal what's going out, which is A1 plus A3. So for the next basic block, X2, this is a simple one. Yeah. Chan, give me X2. A1. Very good. Oops. Equals A2. So we'll just do the next ones, X3. So what comes in equals what comes out. We have X3 equals A2 plus A9. Yes, very good. Equals what goes out, which is A5 plus A4. Yep. X4. This is a pretty simple one. Yeah, okay. All right, Jones, it's all you. A4 equals very good. A6. Now, X5 equals, what do we got? This is super simple. Yep. X6. Jones, and that last one, what comes in has to equal what comes out. So we have A6 and A8. Yes, very good. Equals A9. Now, Elliot, you give me the last two. A5, A10. Where's my X7? Yes, correct. AX8 goes A3. Yep, great. Look at that. Easy exam grade, like points. So logical constraints. This is a bit tricky. So to sort of look at what the code's doing, it takes in some sort of a sequence search. It takes in an array and is looking for a sequence. So I'm guessing it's looking for a subset of the input array. So while found, it's going to look for a set of 3. It's going to try and loop for 3 times while found equals 1. Or it's going to try, yeah, so, oops. So what it's trying to do, I think, from looking at the title of the function, is that if we pass it an array of 1, 2, 3, 4, 5, 6, 7, it's got to be of length 10. So we have 5, 6, 7, come on, give me my pen, where's my pen? 8. And then if we pass in, this will be like num sequence, we can pass in like 2, 3, 4, and it needs to try and find the sequence 2, 3, 4. Will we just now, that question be based on our, no, so like the logical constraints are different to the control flow graph. These are, the logical constraints are pretty much taken directly out of the code. But if you drew a wrong, yeah?
So just to check, let's say if like just now our drawing, let's say this drawing, sort of draw wrongly, like we missing one arrows or something, like A8 is missing. So let's say just now when we do the equation thing, is based on, we do it based on our wrong diagram, will we be penalized for that part?
Yeah, so if you did the wrong control flow graph, like if you missed an arrow, I'd deduct a point there. But if you did the correct, like if you took all of the correct constraints from what you drew, then I'd probably give you full marks.
As in,
Right?
what I mean was the drawing was wrong.
Yeah, so like if you were
Yeah.
missing A3,
Yeah.
and I would give you -1 point here, so you'd get like -1 here. But if you drew all of the correct constraints for the one that you drew,
Yep.
then I would say that's fine.
Okay,
You
so let's say
get full
if
marks.
we got a -1 here, right? Then just now the part where we do the equation, the A3 x something equals to something plus
Yeah,
something,
yeah.
right? Let's say if that one was based on our wrong answer, will that question minus any marks?
No, I
Like
don't
this one.
think so. That's what I'm saying. Like I think as long as you give me the correct constraints for the block for the control flow graph you drew, it should be fine. As long as you obviously didn't draw a graph that was like one basic block and then you gave me one constraint. But like if you're missing an edge and then this you've reflected that you've written your constraints off of the graph that you drew accurately, then it's done correctly. But you obviously got the previous one a bit wrong.
Okay.
Right?
Okay. Thank you.
Yeah. So okay, so let's go back to trying to figuring out these logical constraints because they're a bit tricky.
So sorry, sorry to disturb, but I think part C, you got one of the equation you typed wrong. For x7, it should be x7 equals to a5 equals to a10, not plus a10.
Ah, yes, this is I did. There we go. And this one I did the same.
Oh yeah, yeah. Thank you.
No worries. Good catch. So logical constraints. We have to try and figure out what this code does, and this is not easy. So we can imagine that we're looking for a sequence. Worst case, like best case, our sequence, if we just think about this on purely, it's best case, we get our sequence here. Worst case, it doesn't exist. So best case, worst, best case, BB1, or best case, BB, BB3, no, BB2, or X2. Let me just quickly think about this a bit more. I see how it works. Okay, so the code takes essentially this guy. It steps from 1 to 8, and then it checks the next 3. So it does iterations like this. It'll take 1, and it'll do the next iteration, and it'll go up here, and then it will go and do this. So this little 3-step is this loop here, this while. This is the one that's doing the 3, and then it's doing 8. So it's going to go in this sort of this pattern of doing 3 over like 8, right? So best case, we run x1. Oops, this is a terrible color. Best case, x1 equals 2, because we essentially go down, do the condition, we then set found, we set found to 1, so it'll go back up to BB1 to evaluate for a second time, and then it will keep going. We'll also have, best case, that x3 equals 4, because it will evaluate 1, 2, 3, it'll found a sequence, and then it will leave. So we could say worst case, x1 equals 9, because it will go 1, 2, 3, 4, 5, 6, 7, 8, and then it will, like, it'll evaluate the first time and the last time. So it's essentially the amount of iterations plus 1. So we'll have x1 equals 9. And therefore we can say that worst case, x3, for instance, would be this while loop that does these sort of 3 would run once, twice, 3 times, 4 times, 5 times, 6 times. It will run 8 times and 8 times. So BB3 would run 9 times as well. But then we could go further and do some more constraints, such as like BB4. But this will just be an example of 2. There's a lot of logical constraints you can pull from this. So you could say, for instance, a logical constraint would be 2 is less than or equal to x1 less than or equal to 9, right? And you could also say that, no, you can't say that. Oh, so this is 9 times 3 equals 27. So this is the execution time of basic block 3 and basic block 1. So like here. So this is a bit tricky. And it really just means that you have to understand how you have to think and sit down and look at the code and think about how it executes. What I've done is by looking at this code, if we look at how it actually works, it takes in a sequence of 10 numbers. So we'll just say we have 10 numbers. And it's looking for a sequence of 3. So we can see this from the arguments of the function. We need a sequence of 3. So we can take, this is num, and then we have sec equals whatever. Like we could say 2, 2, 2, and this would never exist. So this is the worst case, that the sequence doesn't exist. Now, if we look at the code and how it actually works, what it does is, is it goes down and it's stepping through, like if we look at this while loop, it's doing 0 to 8. So it's doing 8 steps. And if we look at this while loop, it's doing 3 steps. And what it's doing is that it is checking if the I plus the start index plus I is equal to the sequence plus I. So essentially what it's doing is it's doing loops like this. First loop, second loop. And so this start value in the first loop, start equals 0, this guy. And then in the very beginning of the start loop, we'd go through, and then I is 0 to 2. And it takes essentially start plus I. So it'll take 0 of the number. So it's taking this first one, checking if it's equal to the sequence. So it's checking that it's equal to this one. And if it's not, then it stops. Or, I mean, it'll just keep going. It'll set found equal to 0, and that will break this while loop here, right? So it will do these 3 every time actually though. So it's going to loop like this. So its execution keeps going in this sort of, this loop, if this makes sense. So the worst case is that our sequence is not in our array. Meaning that we run this while for, we run BB1, which is this while loop. Worst equals sequence not in num. Meaning we run all of these loops. Therefore, BB1 runs 8 times plus that final time to terminate. So we'll essentially go, you can see it on your control flow graph. You'll go something like this 8 times, and then you'll exit that one more time. So we'll get BB1 will execute, worst case, 9 times.
So could I ask a question?
Yeah.
So if in this case we're looking for a sequence, right? Why will we even need to check for the second or third number if the first number doesn't match already?
We wouldn't need to. I could probably write a more intelligent code.
Yeah, we
but this code does.
Yeah, okay.
This is not optimal code.
Right, okay,
And
got it.
sequence, to answer Chan, sequence is just random what I did. This is worst case because sequence doesn't exist in num. Therefore, x1 runs 8 plus 1 times. So this is the final sort of termination check thing, like when you have to go back up to a while loop the last time to exit, sort of thing, right? Best case, sequence equals 1, 2, 3. Meaning we come down to while, we run B1 once, then we do this, and it will find the sequence, and then it will go back up to while and exit. Meaning that best case, x1 equals 2. And this is what I've done here. I've just done the best and the worst case, and therefore I know that x1 has to be between 2 and 9. I can't have, because the best case execution, best case scenario, my sequence is 1, 2, 3, which if we look at the code, means I come down to this first while loop, which I'm guaranteed, the first time I'm pretty much guaranteed to go in because the conditions are set that I'm going to go in. I'll go into this while loop that checks for the sequence. It will find the sequence and it will then exit back up to the while loop for the second time, but found will be set to 1. So it will then exit the while loop down to BB8. But it has to run 2 times because you have to go back up to the while loop to exit, meaning that the minimum execution time of x1 is 2. And so this is a logical constraint. And we can do other logical constraints, for instance, for BB3. Because BB3, best case, I run it once essentially to check for my sequence. My sequence is directly there. So I go into it, I run it once, twice, 3 times for my sequence. When I'm not going to run it 4 times, I'm going to run it 3 times. So best case, my sequence is directly at the beginning of my number array. So it's going to run I equals 0, I equals 1, I equals 2, which it uses to check the indexes. Worst case, I run all 8 iterations of my array, and each 8 times I do 3. So this is also here wrong. This should be 8 times 3, which is 24. So worst case, I have x3 is 3 to 24. Yeah, it goes back and it exits. Essentially, the condition fails. So I equals 0, 1, 2. Wait, should I know that? This was correct, what I had, sorry. 4. Worst case, 8 times 4. So this is actually 32. It is 4, JS. My bad.
So
Yep.
can I check with you for the value at the bottom that you wrote, right? The x1, therefore you wrote x1 is equals to 8 plus 1. Can I check with you that this value 8, right? Is it according to the number of colored circles that you actually circled, where
Yeah,
there's
it's
actually
here.
8 circles of it?
Because the algorithm works on going to a number and checking that number and the next 2. And so if you only have 10 input numbers, you can't go to 9 and go plus 2 because there's no more, there's only one more number. So you stop at the 8th. And so this is why this 8 exists here. Like the last check is to go to the 8th index and then to check these 3. Well, like, this is actually the 7th. So this is why you have less than 8, but it's going to run 8 times. It's going to go to the 0th index, the 1st, the 2nd, the 3rd, the 4th, the 5th, the 6th. So it's never going to be able to do more than those iterations. Start will only ever have, this will be the start value, right? This guy here will always be less than 8. So it's going to go 0, 1, 2, 3, 4, 5, 6, 7. So worst case, start goes 0 to 7, meaning that you get this 8 plus 1. So you'll do the while loop 8 times and you'll go up the last time to check before you terminate.
So what you're saying is that it will check for the value of 0, 1, 2 until 7. So total there's actually 8 times that is checking. But why is there a plus 1 again? Sorry.
Yeah, because imagine the first time you do 1, you're checking, like this is the first loop, these first 3, and the last one is these last 3, right? So you're doing like the indexes you're accessing is the 0th index here, then the first, then the second, right? We have 1, 2, 3, 4, 5, 6, 7, 8 accesses. And then we're going to go back up to BB1 and it will fail. And then we'll go to BB8. But we need this last check because we saw when we're drawing we're drawing these graphs here, for instance, we need this last check back up to the while loop. We don't just jump down. This is a no-no. We have to go back up one last time to the while loop, the condition, to check if it's still valid.
Okay.
So it's like the loop plus 1.
So if let's say BB7 to BB8, there's actually an arrow that is heading down. Will that be considered 8 checks or 8 plus 1 checks or just purely 8 checks then?
That would be 8, but you can't have that arrow. There wouldn't be one. You can't do that with a while loop. You'd always have 8 plus 1.
I mean, if we are doing out of a context where we are not doing a while loop, but from BB7 to BB8 when there's an arrow downwards, so there's not a need for us to actually plus 1 because it's not reverting back to the while loop, right?
But
so
a while
it's
loop
just
will
purely
always
check.
do plus 1.
Okay.
Same as this is why we have 4 here. Because this guy does less than 3, but we have a plus 1. So this is 3 plus 1. Because it's this while loop that's going to run 3 times, but it has to do it, like it's going to do the loop code 3 times, but it will do the check, the conditional while check 4 times. Because the last time it's going to exit. Right?
So I say again, sir. So what you're saying is that for the while loop where I is less than 3, so it's checking the value of 0, 1, and 2. Then after that, it will actually do one more check, which is heading back to the while loop from there.
Yeah, so this while loop BB3 will do BB3's checks. BB3 checks 0. And then this is good. 1, good. 2, good. 3, bad. And then, so these ones, it'll go to BB4. And this one, it will go to BB7. Right? Yeah. Yeah, so we can see this on here as well. This is this 3 to 7 or 3 to 4. Okay, so
Okay.
for the worst case, right, for the x3, we multiply by 4 because we multiply by 8 is because we are going 8 times back because of the worst case for the first while loop, right?
yeah, so you're running the contents of the while loop 8 times. Like you run the while loops conditional check 9 times, like 8 plus 1. But worst case, you run the actual body of the while loop 8 times. And since you have the body running 8 times, and we know that this while loop gets done 4 times, then it's just 8 times 4, right?
But sir, isn't it you 8 times, then you run 4 times? Oh yeah, okay.
You see?
Yeah,
Yeah.
okay. Yeah, I understand.
Okay. Can you explain the first case, why the best case for x1 is 2? Yeah, so best case for us is that we have the sequence 1, 2, 3, which means, like if we look at our control flow graph to do our best, we'll say, let's take green. So best case, we go down here to the while loop. We get to BB1. So we go, yep, first case, we're definitely going to go in. We go to BB2, BB3, and now we start doing BB3's while loop. So it's going to loop through BB4, 5. It's going to do like sort of this little loop here times 3. And then it's going to exit through a, no, it's going to go to while, No, sorry, it won't even go through 4 and 5. Ignore this. Oh, man. Okay, so it'll go down to BB3. Then it will do BB6. It'll do this 3 times. Then it will go down from BB7 to, do we put this one in? BB7, yeah, it will go down to, then it will go down here to BB7 and go back up to BB1 and then exit because we've found our sequence. And you can see we pass through BB1 twice, which means X1 is 2. Because we have best case, we find it on the first index of start, but we have to come back up after we've found it to do like the conditional check before we exit, because the while loop means you have to go back up and check before we exit, right? Okay, so I think I'm going to leave that one there, like the quickly before I want to just move on because the tutorial ends now, but I'll do one more question with you guys, and that is we want to do another one of these cache ones. So let me see if I can find one that is different. So we can add a new page. Let me see if I can find one. Can even take it from last year's exam that I wrote. If I have the PDF. Doesn't look like it. Here we go. So this is the cache example from this is the question from last year's exam. Okay. So it's in two parts. Let's work through it really quickly. So assume a direct map cache. Great. And let's just say it should always be mentioned, but it's just assume a 32-bit system if I don't explicitly say it, right? If it matters. Because we're usually dealing with embedded systems, and pretty much all modern embedded systems are 32 bits. So if 10 bits are used for the index and the cache capacity is 16 kilobytes, how much additional memory is required in the cache to store the tags? And so what I mean by tags, this is metadata. We were talking about yesterday. So let's draw out our address just to get a visual. I feel this is always the easiest way. We have our offset, we have our index, and then we have our tag.
So I think that I think that we did this question yesterday. I think that the answer would be that the tag is 18. Yeah, 4.2 as well.
How big is a single cache line?
The cache line?
I think this is different.
This
second question is definitely different.
No, it's the same. How many cache lines there are? There are 256 cache lines. Yeah, 4.2 is the same. The size of one cache line is 256 bytes. Yeah. I mean, this is based on my previous answers that I've written down. Yeah.
Sorry.
Tomorrow I'm doing.
Are you sure? So.
Yep, I'm sure. Sure. I think my colleague Chan could probably agree with me.
Oh yeah. Okay. I have to find a different one. So I think this one is also maybe a little similar to what you had, but you'll realize that these questions, there's not really much difference in them, right? Because there's only about 4 or so different variables that I can change, and sort of how I word the question. Oh, shit, is my screenshot thing. How about this one? So this is from 2017's exam. This is also, I think, similar to what we did maybe yesterday. But we'll do it anyway, because otherwise I have to come up with... Is this... Do we also do this?
Yeah, I think we also did this.
Okay. Then let's just change it a little bit. So we'll just say, for instance, tag of 12 bits. Actually, let's make it a bit, yeah. This might not work, but it should. But we'll just get different answers, so we can work through it differently. But you can probably expect something like this. And I imagine if you do it more than 2 or 3 times, you should be fine for like any question I can ask you. So then look at A. How many instructions can be stored in the cache? So this is essentially just asking how large is the cache, right? Because all the answers to the question will just be answer is size divided by 4, right? Because 4 bytes equals 32 bits. So how big is cache? Can anyone tell me? No. So we know that we have a 64-bit line size. So this is 64 bytes. Now we need to know the number of lines. And how do we figure out the number of lines? Could be. Let's have a look at our address. So our 32-bit address. We have a tag of 12 bits. We have a 64-bit offset, like an offset for a 64-byte line. So therefore, offset is 0 to 63. Therefore, it is, what's that, like 5 bytes? 0, 1, 2, 1, 2, 4, 8, 16, 32. 5, yeah, 5 bits. Therefore, our index, is 32 minus 12 minus 5 bits. So what's that, like 50 bits? So we have 15 bits, correct? Meaning, therefore, we have 2 to the 15 lines. So a few more than 5. We have 32,000. So from this, we can go and say 32, so this is times by 32,768. Meaning that our cache size is 2,000 or 2,000,000 97,152 bytes, which is, I think, 2 gigabytes.
So can I check with you, for your offset, isn't it supposed to be from using from 0 to 63, which is 6 bits instead of 5 bits?
1, 2, 4, 8, 16, 32. Oh, yeah, it is 6 bits. My bad. Good catch. So this is 6 bits. Therefore, this is 6. So we have 14 bits, meaning we have whatever that is, 2 to the 14. 16,000. So we'll have a 1 megabyte cache. 4 times by 64. 1,000 or 1,048,576 bytes, which is about 1 megabyte of cache. Therefore, it can hold whatever this is, 1,048,576 divided by 4. It can hold 262,144 instructions. Right? That's A done.
Sir,
Mhm.
can I check with you for your second line that you wrote? You wrote that the answer is actually size divided by 4, right? So, how do you actually get 4?
Because we have 32-bit instructions, and 32 bits is 4 bytes. So we know that if we want to see how many 32-bit instructions I can store, it's saying how many 4-byte chunks fit into my cache, meaning it's cache size divided by 4. So that's why I've got this.
And 1 byte is 8 bits, right?
Yeah.
Okay, so what you're saying is that for 1 byte it will be 8 bits. That's why we can just 32 divided by 8. We just get 4 bytes then.
Yeah, like an integer in
Okay.
C is 4 bytes. It's a 32-bit value. And so when we come to B, we've already done this. We have already done B to figure out A. So we can just say, yeah, we have 2 to the 14 lines. This calculated up here. From our index, we figured out we have a 14-bit index. Therefore, we have a 2 to the 14 cache lines. Okay, now coming down to C. Now this is a slightly tricky bit. So this is what this is asking is cache size plus metadata. Now we said we have a 12-bit tag, meaning that every line has to store 12 bits. So we have a 12-bit tag. Therefore, each cache line, each of our 2 to the 14 cache lines needs to store 12 bits of metadata. Therefore, our total metadata is 2 to the 14 times 12 bits, right? So this is important to write, make sure we don't write bytes. We want to show bits. 2 to the 14 times by 12. So 196,608 bits. Divide this by 8 is 24,576 bytes. So therefore, to answer the question, What is the amount of memory required for implementing such a cache? We know we want the cache size plus the metadata. We figured out that our cache size is 1,448,000. This is the cache size here, right? 1 million, come on. Therefore, implementation requires 1,048,576 bytes plus 24,576 bytes. Means you need 1,073,152 bytes to implement a 1 megabyte cache with a 12-bit tag, essentially saying a 1 megabyte cache with a 64-byte line and however many lines, 2 to the 14 lines, whatever that was. We all good with this?
So you might have one extra number.
Where?
Oh no, correct. Sorry, I saw wrong. Sorry, you're right.
Okay, great. So I'll save this. Yeah, so this will be uploaded. I'll do this next week though. And also the uploading of these tutorials will happen in the next few days because we have to find out where they get saved to because of the X-Site Zoom stuff. It's weird. But if no one else has any questions, I am desperately in need of a beer.
Sorry, sir. Could I ask just one other question? So the format of our paper, right? It will just be long questions after long questions. So it'll be like 5 of these long questions. I'm just talking about the structure of the paper.
No, so I mean, the way I do them is a bit different. Usually it'll be some sort of like multiple choice at the beginning.
Okay.
Oktoberfest is unfortunately not happening, but there'll be some sort of multiple choice, and then I'll ask you for sort of like, for the C programming stuff, it might be a lot more sort of like quick written answers, like explain to me what a pointer is, and just give me 2 sentences saying a pointer points to a memory address, right?
Right.
But then like there will be a mix between theory questions where I want you to explain something, and then also these sort of like exercise questions where you actually have to calculate or draw something, right? So it'll be a bit of a mix.
Okay, got it.
So you'll need to go through, and for instance, like on this practice exam, you can draw inspiration from sort of like these questions. Or a good question would be, what are the 5 stages of a basic 5-stage pipeline? Like, what are they each? We have like the instruction fetch, instruction decode, instruction execute, and write. There's another one I can't remember. This is not my field, right? And so like this would be a good question.
Oh, okay. So that means that it will probably be a closed book exam, right?
Yes.
Okay.
And to answer Chen, what I generally do with my students at TUM that do a similar course to this where they use FreeRTOS, I will give you a code snippet of C code or FreeRTOS code and ask you what's the result or what's it doing. So it might use a queue, and you have to sort of then look at the code, understand what it's doing. Like it won't be as complex as this code chunk. Like it won't be algorithmically complex, but it will include code that you should have understood or used in the tutorials. So we didn't get super far in the tutorials, but we made some tasks. We used queues to send values. We used semaphores, so you can sort of expect this sort of stuff to come up in the exam.
So basically, let's say, will that question like create this structure or something? Please write this code. That kind of thing happen? No, right?
Yeah, like an example might be, I will give you a code snippet. And then like I'll have a structure that I've created, and maybe I created a point to the structure, and then I'll leave a blank where I'm accessing the member and say, what do I use? Do I use a dot or do I use an arrow? And you need to be able to tell me, oh, he's got a pointer to a structure, so he needs to use the arrow dereferencing operator.
So basically,
we used a lot.
It won't test us like the whole coding. Just maybe like just fill in the blank where you just either you like what you said, just either use a dot or an arrow, that kind of thing.
Yeah, I mean, like, so that you can you have to be able to understand the code,
Okay.
right? Okay. Cool. Any more questions?